Evaluation of muscle activity for loaded and unloaded dynamic squats during vertical whole body vibration. Tom J. Hazel, Genji A. Keno, and Jennifer M. Jacoby. Exercise Nutrition Research Laboratory, School of Kinesiology, Faculty of Health Sciences, the University of Western Ontario, London, Ontario, Canada. We're going to skip the abstract for now. Introduction. Whole body vibration, W.B.V, is a relatively new exercise modality gaining significant interest in the health and fitness realm. This type of exercise typically involves individuals performing traditional resistance exercises on the platform with their body mass as resistance. Although there is a wide range of exercise protocol used, the positive results of W.B.V studies report enhanced strength, power, and endurance and blood flow in working skeletal muscle. However, there are reports to the contrary suggesting no training benefit of W.B.V exercise. Regardless, there are many studies indicating that exposure to W.B.V during static and dynamic body mass exercises increase exercise intensity. The mechanical vibration generated by the W.B.V platform are thought to induce length changes in extrafusal fibers, resulting in the activation of an afferent feedback response through the muscle spindles, and 1A afferents a response akin to the tonic vibration reflex, TVR. The mechanical vibration stimulus may also affect skin and joint receptors that provide sensory input to the gamma motor system, increasing the sensitivity and responsiveness of the muscle spindle to further mechanical perturbations. The W.B.V perturbations put a high level of stress on the muscular system that requires high levels of neuromuscular activity. Recently, electromyography, EMG, has been used to characterize muscle activation, and previous literature has demonstrated that exposure to W.B.V results in an increase in leg muscle EMG activity. Our group has even shown that exposure to W.B.V increases EMG in the lower limbs, but has little to no effect on the upper limbs. The discrepancy may be the result of the proximity of the muscles to the vibration stimulus and the distance from the platform, the dampening of the stimulus in the upper body because of the body position, or the effect the body mass has on the loading of lower limbs. If W.B.V induces a TVR response, then increasing the sensitivity on the system may result in a greater W.B.V response, because it has been reported that the sensitivity of 1A afferents is increased in response to an increased preceding level of muscle activity. Furthermore, from a biomechanical perspective, W.B.V exposure increases exercise intensity by increasing the accelerations of the body because force equals mass times acceleration. Increasing the mass at a given acceleration W.B.V stimulus, the resultant should be the increase in force. Although EMG is not a direct measure of force, the two are strongly correlated. So many increase in force should be represented by an increase in EMG. Therefore, the addition of a light load should increase baseline muscle activity, pre-activation, and potentially increase the sensitivity of the 1A afferents, leading to an increased magnitude in the previously demonstrated W.B.V induced increase in an unloaded condition. The purpose of the study was to examine the muscle activity in the lower limbs during unloaded and loaded dynamic squatting with W.B.V. We hypothesize that the addition of a load to dynamic squatting during W.B.V exposure will augment the W.B.V response compared with the same condition with no additional load. Methods. Experimental approach to the problem. This study investigated whether the addition of a light external load could augment the W.B.V-induced increases in muscle activity seen in response to dynamic squatting with no load. Electromyography was used to measure changes in muscle activity, dependent variable, in the vastus lateralis, VL, bicep femoris, BF, tibialis anterior, TA, and gastrocnemius, GC. Muscle activity was assessed during loaded and unloaded dynamic squat in the two different exercise conditions, with W.B.V and without vibration. 3 vibratory stimuli were used, 25, 35, and 45 Hz at 4 mm amplitude wave. TM, maximal muscle activation, was also recorded to compare muscle activity as a percentage of maximal. Subjects: 13 recreationally active male kinesiology students, 23 plus or minus 2 years, 178 plus or minus 6.3 centimeters, and 84 plus or minus 11.9 kilograms, volunteered to participate in this study. All were healthy as assessed by PAR-Q health questionnaire. Subjects had no experience with resistance training over the last 4 months. Before any participation, the experimental procedures and potential risks were explained to the subjects, and all subjects provided written informed consent. The study was approved by the University of Windsor Research Ethics. Electromyographic electrode placement. Electromyographic electrodes were placed on the BL-BF-TANG-C over the mid-belly of the muscle, parallel to the direction of the fibers. Before electrode placement, the area was shaved, abraded with coarse fabric, and swabbed with alcohol. Inter-electrode distance was fixed at 10 mm within the prefabricated electrode bar. High conductivity electrolyte gel was used with a reference electrode, R200 biometrics, that was positioned on the lateral malleolus of the fibula. A goniometer was adhered with double-sided tape to the lateral side of the left knee to ensure a consistent dynamic squat, descent to about 90 degrees, ascent to about 160 degrees. Also, verbal feedback was provided to ensure consistent performance of the dynamic squat, and a metronome was used to ensure correct cadence. See details below. Protocol. All subjects performed a familiarization trial employing both the static and dynamic squat to acclimate subjects to the W.B.V stimulus. A demonstration of proper technique for the dynamic squat movement occurred, and practice of this movement was undertaken until performance of the squat was consistent and correct. Electromyographic electrodes were not used during the familiarization session. The vibration stimulus was 4 mm for 3 frequencies, 25, 35, and 45 Hz, applied with a WAVET TM platform. Pardon me. Whole body advanced vibration exercise, Windsor, Canada, that oscillated vertically up and down. We have previously demonstrated an increase in muscle activity with these W.B.V stimulus. The load applied in the study was 30% of the subject's body mass, ranged 20 through 33 kilograms, and was applied using a standard 180 centimeter Olympic bar, about 20.5 kilograms, with appropriate additional weights held behind the neck and resting atop the shoulders and upper back. This load was selected to provide a reasonable and safe weight that untrained individuals could lift without inducing fatigue and ensuring safety. The 8 conditions examined were as follows: no vibration, no load; no vibration, load, 25 Hz, 4 mm, no load; 25 Hz, 4 mm, load; 35 Hz, 4 mm, no load; 35 Hz, 4 mm, load; 45 Hz, 4 mm, no load; and 45 Hz, 4 mm, load. All conditions were randomized within the and between subjects, and the W.B.V frequency and amplitude were not verbally conveyed. With each condition, subjects were required to complete 7 dynamic squats at a cadence of 1 second down and 1 second up, with the use of a metronome with a 5-minute rest period between conditions to prevent fatigue. Platform foot position was slightly wider than shoulder width and was marked on the first trial and used for all further trials. The experimental session was held at least 72 hours post-familiarization protocol, and subjects refrained from exercise or ingestion of caffeine for 24 hours and did not eat at least 2 hours before any visit to the laboratory. During the actual testing session, subjects performed an EMG noise trial to determine the amount of baseline interference with the specific rested supine on the mat with an EMG was measured for 1 minute to determine the inherent noise within the signal. which was then deleted from further EMG signals collected, customized software, see EMG analysis below. Subjects were then asked to perform maximum voluntary exertion (MVE) test for the muscle groups being evaluated. The MVE trials obtained a maximum EMG profile rather than force output measures. Dynamometers were unavailable for all muscles studied. All MVEs were isometric at 90-degree joint angles and were performed 3 times against the resistance provided. An immovable object for the VL knee extension, BF knee flexion, and TA dorsiflexion and the GC plantar flexion muscles. Subjects were provided with approximately 10 minutes rest before beginning the 8 sets of dynamic squats as outlined above. Electromyographic analysis. The EMG signal was pre-amplified by the gain of 1000 and sampled at 1000 Hertz. Datal Log Biometrics Limited, Gwent, United Kingdom. Band pass filtered 20 through 450 Hertz and stored for offline analysis on a 512 MB MMC flash card. The EMG was post-processed using customized software. LabVIEW National Instruments, Austin, Texas, USA. The EMG data were extracted. The start and end points of the 7 dynamic squats per session were marked. The interference EMG was dual past 6th order Butterworth filtered between 100 and 450 Hertz, which removed any noise caused by the frequency of the vibration platform. The data were then full wave rectified and smoothed with a low pass filter at 1.5 Hertz. The noise was then subtracted and the data were divided by MVE and multiplied by 100 for normalization. The EMG Grimm's root mean square was then calculated. Statistical analysis. Analysis was performed using Sigma Stat version 3.5 A4 times 2 repeated measures. Analysis of variance was used to evaluate the independent variables of vibration and load on muscle activity. EMG Grimm's post hoc tests were performed using Tukey's Honest Significant Difference ASD test. Data in the text are values plus or minus standard value deviation, whereas figures were reported as values plus or minus SEM, and the level of statistical significance was set at P is less than or equal to 0.05. Results. Vastus lateralis. There was no significant vibration times load interaction. P is less than 0.172. There were main effects for vibration. P is equal to 0.004 and load P is less than 0.001. During unloaded dynamic squats without the addition of W.B.V, VL muscle activation was 42.5 plus or minus 16% MVE relative to no WVE exposure to W.B.V. In the unloaded condition, increased muscle activity 1.4 through 5.5%, figure 1. The 45 Hertz vibration condition was significantly greater compared with the no vibration condition. P is equal to 0.009. The addition of a load to the unloaded no WBV condition increased muscle activity 3.2% to 9.7 plus or minus 6.3%. P is equal to 0.001. Further increased muscle activity 0 through 3.6, figure 1. The 45 Hertz condition was significantly increased versus the 25 Hertz condition. P is equal to 0.017. Biceps femoris. There was no significant interaction between the vibration and load. P is equal to 0.368, but main effects were evident for vibration and load. P is less than 0.001. During unloaded squats without the addition of WBV, BF muscle activity was 6.5 plus or minus 4.2%. Exposure to WBV in the unloaded condition increased muscle activity 0.5 through 1.7% compared with the no WBV condition. Figure 2, where the 45 Hertz condition was significantly increased versus the no vibration. P is less than 0.001, and the 25% hertz P is equal to 0.008 conditions. The addition of a load to the unloaded no W.B.V condition increased muscle activity from 3.2 to 9.7 plus or minus 6.3%. P is equal to or less than 0.001. Subsequent exposure to W.B.V in this loaded condition further increased muscle activity. 0.2 through 2% loaded condition further increased MVE, figure 2. Compared with the no W.B.V condition where 45 hertz was significantly increased versus the no vibration, P is less than 0.001, 25 hertz, P is less than 0.001, and 35 hertz, P is equal to 0.031 conditions. And the 35 hertz condition was also significantly increased over the no vibration, P is equal to 0.038 condition. Tibialis anterior. There was a significant two-way interaction between the vibration and load. P is equal to 0.030, and the main effect for load, P is equal to 0.008. However, there was no main effect for vibration. P is equal to 0.08 during unloaded dynamic squatting without the addition of W.B.V. TA muscle activity was 34.6 plus or minus 6.9. Exposure to W.B.V in the unloaded condition increased muscle activity. Increased muscle activity 0.1 through 2.3%, figure 3, where only 45 hertz was significantly increased over the 35 hertz condition. P is equal to 0.026. The addition of a load to the unloaded no W.B.V condition resulted a 7.8 increase in muscle activity. P is less than 0.001 to 26.8 plus or minus 6.5%. Subsequent exposure to W.B.V in the load condition increased muscle activity 2.6 through 3.8%, figure 3, where the 45 hertz condition was significantly increased compared with the no vibration condition. P is equal to 0.048. Gastrocnemius. There was no significant interaction between vibration and load. P is equal to 0.15. Although main effects were observed for vibration, P is less than 0.001, and load, P is equal to 0.010. During unloaded and dynamic squatting without W.B.V, GC muscle activity was 7.5 plus or minus 3.2% MVE. Exposure to W.B.V in the unloaded condition increased muscle activity 2.9 through 8.9%, figure 4, where 45 hertz was significantly increased over both the no W.B.V and P is less than 0.001, and the 25 hertz condition, P is equal to 0.042. The addition of a load to the unloaded no W.B.V condition increased GC activity a further 5.9%. MVE, P is equal to 0.04 to 13.4 through plus or minus 8.6%. Subsequent exposure to W.B.V in the load condition further increased muscle activity 6.3 through 9.8% MVE, figure 4, where the 45, 35, and 25 hertz conditions were all significantly increased versus the no W.B.V condition. Discussion. This study examined whether the increase in muscle activity in the lower limbs that occurs with exposure to W.B.V during dynamic squats would be further enhanced with the addition of a light external load. Our previous data demonstrated that W.B.V resulted in a significant increase in skeletal muscle EMG during static and dynamic squats. Our current data confirmed this finding, as exposure to W.B.V with a frequency of 45 hertz resulted in significant increase in muscle activity in all 4 muscles examined. The addition of a light external load increased muscle activity during dynamic squats as expected. However, W.B.V increased muscle activity during both unloaded and loaded squats to a similar magnitude. As expected, the addition of a light external load, 30% of the body mass, increased baseline EMG activity in the VL, about 15% BF, about 2%, and GC, about 6% muscles, but decreased TA activity, about 8%. The decrease in TA muscle activity was unexpected and may have been caused by a slight and non-visual change in center of mass. However, monitored squat technique and posture appeared unaltered. The addition of a load was intended to increase the level of muscle activity and potentially enhance the effects of W.B.V in muscle activity in all muscles studied. The decrease in muscle activity in the TA highlights the importance of body position on the platform. To date, there have been no biomechanical evaluations of body position and muscle activation during W.B.V. This study demonstrates that exposure to W.B.V at 45 Hz results in increases in muscle activity whether performing loaded or unloaded dynamic squats. This result agrees with those of previous studies, all demonstrating a W.B.V-induced increase in muscle activity. However, the average W.B.V-induced increase in muscle activity of all four muscles was 2.5% in an unloaded condition, and a similar 3.5% in the loaded condition, suggesting that the addition of a light external load did not increase the sensitivity of the 1A afferents. Moreover, although the addition of a load increased muscle activity, exposure to W.B.V resulted in a further increase in muscle activity. This agrees with the biomechanical perspective that increasing mass at a given acceleration likely results in an increase in force represented by EMG. Thus, the possibility still remains that the use of heavier loads with W.B.V may increase the sensitivity of the body to the mechanical perturbations, further enhancing EMG muscle activity. This idea requires further investigation. It has been theorized that W.B.V oscillations increase muscle activity via a reflex response akin to the TVR, where 1A afferent activity in the muscle spindles alters surface EMG and a single motor unit activity. Therefore, if W.B.V induces a similar response to TVR, then muscle activity might be further augmented by increasing the preceding level of muscle activity with the addition of a load. The current data demonstrate that the addition of a light load did not enhance the W.B.V-induced increase in EMG activity already demonstrated in the unloaded condition. This suggests the increase in baseline muscle activity did not increase the sensitivity of the 1A afferent, and that the skeletal muscle response to W.B.V may not be as analogous to the TVR as originally proposed. This lends indirect support to the idea that the increase in EMG muscle activity during W.B.V may occur because of greater demands for postural stability, or maybe the muscle's natural response to dampen an imposed vibration stimulus similar to that seen during running. In the practical realm, adding a load to dynamic squatting increases muscle activity in the lower body, with the exception of the TA, and has its greatest effect in the primary muscles generating the squat movement, quadriceps and the GC. The addition of the W.B.V to loaded condition increases muscle activity 3.5% to a similar magnitude because the increase in EMG activity observed in the unloaded condition was 2.5%, suggesting the effect of W.B.V is independent of load. Moreover, although it appears that the addition of the load may cause the greatest stimulus in the thigh, VL, the major effect of W.B.V appears to be on the muscles most proximal to the generation of the W.B.V stimulus, TA and GC. Thus, the unique applicability of W.B.V may be to not only activate the agonist muscles used during a dynamic movement, but to also increase the activation of a synergistic muscles closest to the stimulus in all postural conditions. These W.B.V-induced increases may be the mechanisms resulting in an improved function seen in several W.B.V training studies. The current data, while as young, healthy men, may have practical applications, especially in a rehabilitation setting where the addition of a load to dynamic exercise, typical of resistance exercise, is not yet tolerated. This requires further investigation. Furthermore, it remains intriguing to determine whether the use of heavier external load would enhance the muscle spindle's response and augment EMG activity and muscle function as originally hypothesized. Practical applications. Our findings demonstrate exposure to W.B.V results in a similar magnitude increase in muscle activity during both unloaded and loaded dynamic squats. The effect of using a heavier external load during exposure to W.B.V remains to be examined, as does body positioning on the platform. The results of the study also demonstrate that the cumulative effect of adding a light external load to dynamic squat with W.B.V increases the intensity of the exercise being performed. This supports earlier suggestions that the use of loaded resistance training on a W.B.V platform might be more beneficial than the same training without W.B.V. Moreover, those individuals that are typically discouraged or unable to perform resistance-loaded training are likely to benefit from this combined light-load W.B.V exercise program. This could include athletes who are recovering from an injury or individuals with conditions that preclude heavy weight bearing, bone or joint disorders. Acknowledgement. Mr. J. Court and D. Clark are thanked for assistance with adaptation in the custom design EMG scripts.